When an ANOVA summary is generated from a computer program, for example, it's typically in this form. So this is kind of a general idea of what an ANOVA looks like. So across the top you'll have these values, sums of, or these headings, sums of squares, degrees of freedom, we just talked about that one, mean squares, and F. And then down the side, between and within. So in this first spot here, sums of squares in between, we have SSB, which is the sums of squares between. Degrees of freedom, K-1, we just learned how to do that. And then mean squares, MSB. And then you have within, and this is also referred to as the error in the sample. So sums of square W, so sums of square within. You'll also see sums of squares E here sometimes, depending on the notation or the book. Degrees of freedom, N minus K, we just talked about that, and then mean squared is W. Now, as I mentioned earlier, there are a lot of calculations that go into this. They're not necessarily difficult, but they're a little time consuming, and we're just going to let our computer programs and calculators handle that, but mostly what we're doing here is doing some of the final calculations rather. Oh, okay. Now what I do want to point out to you here is the relationship between sums of squares, degrees of freedom, mean squares, and F, because they are quite related. Now this mean squares between, actually the way I can get that is just taking the sums of squares between divided by the degrees of freedom. So SSB over K-1, that gives you the mean squared between. Similar for mean squares within, or mean squared error, if I take the sum squares within divided by the degrees of freedom, N minus K, that's how I get that MS sub W. And then finally, once I know those two values, if I take the mean square between divided by mean squared within, that's my F. And we talked about that earlier, the variance between versus the variance within. So even if we're presented with an ANOVA table and it's incomplete, knowing those relationships, we can fill in any missing information. So keep those equations in mind, and we're going to move on here to example 3. The expenditures in dollars per student for schools located in 3 sections of the country are summarized below in the Excel printout. So this is a typical printout from Excel. Notice again, we don't have the raw data, we have the summary. So let's say we're dividing the country up into east, middle, and west. And we have counts of 5, 4, and 4, and the average expenditure is 6,091 for the eastern, 6,500 for the middle, and 6,800 for the western. And what we're trying to figure out is, among the sections of the country, are they spending about the same amount per child? Again, you don't want to just look at the numbers and make that decision. Yes, looking at the West, it looks like the West is spending more per child than the Eastern, but you also have to take into consideration the size of the sample and the variance, because the variance can affect, is that really a significant difference, or is it not really a big difference at all? So don't just look at the numbers and say, yeah, because you really don't know until you back it up with some statistics. Okay, then the rest of the ANOVA table is printed down here, but it's incomplete. So it's going to be our job to fill it in. Now remember, degrees of freedom comes from the number of categories, or groupings rather, or knowing the big sum of all the data minus K. So we can figure those two out, degrees of freedom. So here between, remember, is K-1. Well, we have 3 groupings, eastern, middle, and third. So this is going to be 3 minus 1, or 2. And that's our degrees of freedom numerator. Then for within, for capital N, we add the size of the sample groups for each, or the size of the sample for each group. So that would be 5 plus 4 plus 4, or 13. So to get the degrees of freedom, that is N minus K. That's 13 minus 3, not the previous degrees of freedom, but the number of categories. So that would be a 10. And I guess you can do a total down here. I don't know that it's, well, we'll go ahead and add those together. We might not use it, but it doesn't hurt. Okay, so we found the degrees of freedom. Now, we would not have been able to do that had we not had the summary above of the number of categories we had and the sample size of each category, so that information was important. But now that we know the degrees of freedom, we can find the mean squared. All I have to do is take the sum of squares divided by the degrees of freedom. So for MS between, this is going to be this very large number here, divided by 2, and I get 6222294, so 622,294. And the same thing for within. I would take sum of squares and divide it by degrees of freedom. And here I get 95914.5. And somehow this is missing, but we also want our F value. Well, now that we know the mean squared between and the mean squared within, which is also called the mean squared error, if I just take the ratio of those two, then I have my F value. So I'll take my 622,294 divided by, 959,104.5, and that should give me my F, and I get 0.64882, which is probably plenty of decimal places. Okay, so now that we've completed our ANOVA table, including the F value, we should be able to answer some questions down here. Part A, what is the p-value corresponding to the F statistic for the ANOVA test? The p-value, if you remember, is a probability of getting a value at least as extreme as the F value that we got. But probably it makes more sense to think of it this way. Now this time, notice this time we didn't compute a critical value, but we did compute a test value. That F value we got, 0.64882. And that's probably back here somewhere, 0.64882. So the p-value is asking, what is this area here? That's the p-value. And you can't find that on your table. You have to use some technology to do this. So either you can use your calculator or you can use the ALEX calculator. Now if you choose to use your TI-83 or 84, you would go into calculator instructions. You would go into your distributions, like where you're used to going for your normal and binomial and all that stuff, and arrow down until you see capital F CDF. And the most difficult part probably about these is remembering the argument. The argument, because it'll put FCDF parenthesis on your screen. You want the lower bound and then a comma, the upper bound and then a comma, degrees of freedom numerator, comma, degrees of freedom denominator. And that's kind of a lot of information, but all of that is necessary. So for me, lower bound and upper bound, I think of this as left and right, if that makes it easier for you to think about it. So in your calculator, once you have that FCDF on your screen, our left bound would be 0.6482, the F value that we have. But because I'm going into the tail, and the tail is going to continue forever, that's infinity, so you want to use a really large number like 99999. Our degrees of freedom numerator, we filled in our table and said that that was 2. And our degrees of freedom denominator, we said, was 10. And you should get something pretty close to 0.543326. And we were asked to round to 3 decimal places. So we could say 0.543. So that number represents this area here that is to the right of 0.6482. And so that's what you would type in for your p-value. And then in part B, they ask us, at the 0.05 level of significance, do you conclude that there are differences in the mean expenditures per student for the 3 sections of the country? So this is where you want to compare the p-value to alpha. And pretty much the way it goes, and this is kind of across the board for all of our hypothesis testing, is if the p-value is low, then the null has to go. Well, 0.54 is not lower than 0.05. It's actually larger. So since 0.543 is larger than alpha equal to 0.05, we fail to reject H naught. And I know the p-value is a little confusing for some of us, but the p-value is that area beyond the f-value that we found. This is kind of extra. This is not a part of the problem, but if you're a little more comfortable with finding regular f-values and comparing them that way, we have f of 0.05 is alpha. Our degrees of freedom are 2 and 10. So let's look that value up. 0.05, let's go up here. Okay, there we are. 0.05 degrees of freedom were 2 and 10. So there we are right there, 4.1028. If you think about your picture, skewed in the tail, 4.1028. And this would be the rejection region down here. So this is the traditional way of doing it if the p-value is a little bit confusing to you. And you can always do this even if it's not asked for. So we're supposed to compare what we got for our f-value to that 4.1028. Well, our f-value was 0.64882, which we know is way back here because it's less than 1. So because my test value is not in the rejection region, I would get the same conclusion. We fail to reject H naught. So whether you do it by p-values or whether you do it the traditional way by comparing the test value to the critical value, you're going to get the same thing, but just make sure you understand what's being asked for with the p-value. Okay, so no matter how we did it, we said we failed to reject H naught. What does that mean in the context of a problem? That means all of our means are the same, but specifically, that means the expenditure per student is roughly the same. So for part B, where it says, do you conclude that there are differences in the mean expenditures per student for the 3 sections of the country, your answer would be no. So since we failed to reject H naught, the mean, well, I should say it this way. You got to be careful in statistics. There is evidence to suggest since we're accepting the null, that the mean expenditure per student for the different sections of the country are the same. Statistically the same. Numerically the same? No, but statistically the same. So for part B, is there a difference? My answer would be no. Be really careful there. Those questions, the way they're worded, you can kind of get caught up, even if you've done all the work correctly, you can kind of get caught up in how the question is asked versus what you're trying to answer versus what you got when you rejected or failed to reject. So be very, very careful and double check that part when you're doing your homework.